Hello, everyone. Today we are going to talk about category theory. Professor Vero asked me to solve some examples in category theory for you, so you would get used to it more. I think Professor Vero already has talked about category theory a little bit, but I'm assuming it's something new for you. If you had any course which is related to set theory or abstract algebra, would you raise your hand here? I just want to know if any of you have experience of reading something in algebra about groups, rings, or even set theory. Do we have anyone? Okay, apparently not. Okay, so today I'm going to speak more about category theory. Category theory. So category theory is kind of, you can think about it more as a language or a formalism in mathematics, which kind of tries to unify different parts of math. It's like looking for a global language to formalize mathematics. So I'm not specialist in this field, but I think my understanding is that if you look at different areas of mathematics, although they are different, it seems they have a lot in common. Sometimes if you're studying geometry, or if you're studying algebra, or if you're studying number theory, or if you're studying a lot of different fields in math, you would get the sense that although we are working with different objects, we are proving theorems about different things, it seems they really kind of look like each other. It's like, for example, when you are doing algebra and when you are doing geometry.
So wraps it up for the notable hands played in this one. It was
sorry. When you study these different fields, you would get the feeling that they are very similar. And it seems they have a lot in common. It seems there are theorems in different parts of mathematics, which they are true really independent of that specific field in some sense. You would see that as you progress in mathematics, you would see a theorem in, for example, algebraic topology, and then you would see a theorem in algebraic geometry, and then you would see another theorem somewhere else, and you would feel, oh, these theorems, they really look parallel to each other, right? Although they're about different objects. Okay, I'm just talking now. I don't expect like you really would know what I'm saying. But that's the goal of category theory, kind of find the analogy between different fields of mathematics. It's kind of like a language for different parts of mathematics. It's not necessarily true that every mathematician should or would use this language. Maybe if you ask a person who is doing differential equations, or is doing probability or statistics or number theory, they might not use this language, but it's a good thing to know, especially if a person wants to do things related to algebra, algebraic geometry, many parts of pure mathematics. This language proves to be a very strong tool. And apparently, if someone, for example, wants to do modern algebraic geometry, it's really necessary to use this language. So let's get into definitions and examples to get a better feeling about it. So, of course, let's start with the definition of a category. What is a category? So a category is, so a category, the definition of category is this. Category consists of two things. One is a collection of objects. And the other is a collection of morphisms. So one way to think about a category is just it's a collection of some objects. I show each object with just a point. So for example, our categories, say we have a category C, it has like 7 objects. Let's name them. Let's call them 1, 2, 3, 4, 5, 6, 7. And a collection of morphisms. A morphism is, well, you can think about it something like a function. You can think about it as a map which has a domain and codomain. It goes from one of these objects to another object. We show these morphisms with just an arrow. So for example, here we have an arrow from 1 to 2, 2 to 3, 5 to 4, from 6 to itself, and etc. Each arrow, you can think about it as a function or as a morphism from one of these objects to another one. Maybe it's better to call them A1, A2, A3 rather than just 1, 2, 3. You can think about them as something like sets. For example, each AI can be a set, okay? Just a subset of, for example, natural numbers. And each arrow can just be a function from subset of natural numbers to another subset of natural numbers. But they are supposed to satisfy a few properties. One is that each object should have a morphism called identity morphism. So for example, here for each AI, we should have a map from AI to itself. We would show that with identity of AI. For example, if these AIs are sets, this is just a map which correspond to each element of the AI itself, okay? That's how we define identity map. If I want to use this arrow-like notation, it means for any AI here, I should have a map which starts from AI and it ends up at AI itself. For example, we have identity of A1, we have identity of A2, identity of A3, identity of A4, identity of A5, identity of A6, and identity map of A7. So for each of them, we have a map which starts at AI and it ends up at AI. We show it with a loop because the domain and codomain are the same. You know, whenever we have one of these maps which start at one point and ends at another point, one of these arrows, we call this first object, the beginning point, we call that domain, as you know in like calculus or elementary mathematics. And the final point is called codomain. So when we have identity, it's a map from an object to itself. So here, domain and codomain are the same. Domain is the same as codomain. And the second property is that whenever we have two of these arrows, we need to have a composition of these two arrows. So there exists something called composite morphism. It simply says whenever you have a map from between two objects, for example, let's call that F, and another map between two other objects, G, there should be a morphism which is composition of these two, which we show that with GOF. So again, in this figure we have here, we have A1 going to A1, and then a map goes from A1 to A2, right? Or, well, maybe I should use another color. See here, I have a morphism going from A1 to A2, and another morphism going from A2 to A3, right? There should be a composition of these two. So there should be an arrow going from A1 to A3. Okay. Now, so that arrow should exist. That's the definition. Now, there are a few properties these things should satisfy. One is that, well, basically there's just one. So for any object here, I said we have this identity morphism of that object. Okay, now suppose there is another object and there exists a map, there exists a morphism or an arrow F between them. So one can look at the composition of these two things. One can first look at the identity morphism and then apply F. This thing should be equal to F. This is again part of the definition. And that's actually, that's compatible with the definition of identity which we have in mind, right? Also, we might have a morphism F between two objects, and then we can have, well, we would have the identity at codomain. So first we have F, and then we have identity. And their composition again should be F. This is part of the definition. There is one more property about categories, which is associativity. That means if we have, for example, 3 objects, A, B, C, we can have, 4 objects and D. And suppose we have a morphism F from A to B, a morphism G from B to C, and a morphism H from C to D, okay? Now, the properties of a category, the definition of a category says when we have F and G, there should be the composition of F and G, which is G, O, F, right? And now that we have G, O, F and H, there should be composition of these two, which is H, O, G, O, F. Now, on the other hand, when we have G and H, by definition of a category, we should have composition of G and H, which is H, O, G, right? And again, we have H, O, G, and we have F. So we should have the composition of these two, which is H, O, G, O, F. Now, associativity tells us actually these two things are not two different arrows. They end up to be the same arrow. So H, O, G, O, F. If we first compute H, O, G, and then apply F, should be equal to H, O, G, O, F, where here we first compute G, O, F, and then H. So I would erase this other green arrow because that's the same as the blue arrow we have down there. They should be equal. So this thing is actually equal to G, H, O, G, O, F. That's just the definition. So any couple of points they give us and some arrows between them, if they satisfy these properties, then we would say it's a category. Okay, so for example, let's look at another example. If you have some objects here, for example, if they tell us, is this thing a category? We would say no, because this element here does not have the identity map. There should be an identity map here too. If we have another collection of elements, and we have this arrow, this arrow, this arrow, this arrow, they would ask us, is this a category? The answer would be no, because we have a map from one element to the other, and it follows from another morphism, but there are no composition, right? And also, now we have this blue arrow, and then a second arrow following that to that final point. We should have their composition too. So and then everything, of course, has this identity arrow from itself to itself. So any collection of elements with these properties is called a category. Okay. Is there any question up to this point?
Can you have multiple morphisms between the same two objects?
That is true. You can have many morphisms between two objects. You can have even many morphisms from an object to itself, which they are not identity. You should have identity, but you can have a lot more. That is correct. Yeah.
Thanks.
Yeah, sure. So that's just the definition. Okay, we should see what it means in practice. So the point is that let's look at some examples. So maybe the most basic category one can have is a category C with just one object, say just one object, and the morphisms of this category, which are the morphisms from this object to itself. I would show it like that. It means morphisms from, I have just one element, I'm showing it with just a point, with a dot, and I'm looking at the morphisms from this thing to itself. Oops, sorry. The easiest case is that there exists just one morphism, and that's the identity of that object. And this is how this category would look like, right? Just one object and one morphism. Maybe the most important example is the category of sets. We usually show it with just S-E-T. This is the category of sets. What are its objects? So for any category, I should tell you what are the objects of that category. And then I should tell you what are the morphisms between any two elements, any two objects in that category, right? So the category of sets, as you can imagine, the objects of this category is, well, the object. Can anyone tell me what are the objects of this category? Can you guess?
I guess they're just sets.
Yeah, but all of sets, right?
Yeah,
so,
every set.
So all of sets. But it's a little tricky. We are not doing fundamental mathematics here, but it's wrong to say set of all of sets. So I'm not going to say set of all of sets. I'm just saying the collection of all of sets. So you can have set of all even numbers. You can have the set of natural numbers. You can have a lot of things, but there is no set of all of sets. And it's a pretty interesting thing. Maybe a little counterintuitive, but we ignore that. And then for any two sets, so for say A and B are just two sets, for any two sets A and B, we should say what are morphisms between these two sets. And what are the morphisms between these two sets? The morphisms are all functions, so all functions you have, all functions like f you have from A to B. Every function from A to B. Okay. Now we should see why this thing satisfies the criteria of being a category. Here I've introduced objects. I've introduced the morphisms between two objects, which are just set of all functions from one set to the other one. And now I should see if it's really a category. So let's go back to the definition of category. What are the properties it should satisfy? Well, every object should have identity element. So for any set A, there should be an identity element. Well, there is. We have identity map from any set to itself, which identity of any point x is equal to x for any x inside this set A, right? The identity map should satisfy this property that if you have a set A and another set B, if I look at the identity map first from A to itself, and then the function f from A to B, if I look at the identity of A, well, maybe it's better to use subscript A for the identity of A. And look at this composition with f, it should be equal to f. And this is correct, right? Because for any x, f o identity of A of x is equal to f of identity of A of x. But identity of x is just x, so it is equal to f of x. And when that's true for all x, because it is true, it's true for all x in A, it means FO identity of A is equal to F. We have a similar theorem for identity on the left side, identity of B or F. So similarly, identity of B OF is equal to F for any F. That's correct too. Again, we have composition of functions on sets. We know that, right? If you have any four sets, we know if we have F, G, and H, we know we have associativity for these things. For sets, it is correct. Sorry. So we know for sets we have HOGOF equals to HOGOF. And so these are the properties we have for sets. We know that they're kind of trivial. Therefore, we have category of sets. So this is kind of the first important category we have, category of sets. So most of the other categories we would see are kind of related to this category. So let's go to the third example. Raise your hand if you know the definition of a topological space. I want to know if we can assume here that you know that one or one person.
I mean, maybe I could.
Okay.
Okay, fine. So a topological space is obviously a space where you endow topology. That is a set of open sets such that it contains the empty set and the entire space itself. And the union of any two elements of the topology is also in topology. And I think there's a third property, but all finite unions are members of topological sets. And there's some about infinite intersections. I'm not sure. But that's all I can recall.
Okay, that's good. That's great. So maybe I can modify this a little bit. So suppose we have a category C, which its objects are subsets of R. Any subset of R, anything which is a subset, like intervals, like R itself, like anything. And then the morphisms between two subsets of R, say A and B are two subsets of R, A and B are subsets of R, are the set of maps from A to B with this extra property that the map is continuous. Okay, so the morphisms are the set of continuous maps. Now the question is that, is this a category or not?
I think it is, but I just had a brief question. I
Yeah.
think that sometimes you're not going to be able to have like continuous maps. For example, if A is just null, if A is just say zero and B is in any anything is like all of R, then there's going to be no map at all. Morphisms don't have to be defined between all objects in a category, do they?
Okay, yeah, let's address that. So let's first see if here this thing is a category or not, and then think about your question. So for this, in order for this thing to be a category, we should have two properties. First of all, for any subset of R, like A, we should have an identity map from A to itself. So is this identity map, do we have it here? Yes, we do, because identity map is continuous. So identity map is always, well, with the way we know R, the way we know the set of real numbers, we know that the identity map is continuous. So the identity map is a morphism here. So we have the identity map. That's good. Also, again, we know functions satisfy associativity. The other thing before that, one more basic thing here we should check is that if we have a map from A to B and we have a map from B to C, we should have a morphism from A to B and a morphism from B to C. By morphism, I just mean this arrow we are using. I try not to use the word map or function. Morphism is a more general concept. We should have a morphism GOF. Do we have that here? We do. Why? Because if F is a morphism here, it means F is continuous. If G is a morphism in this category, it means G is continuous. And we know when we have two continuous functions, their composition is also continuous. So GOF is continuous, and therefore it is a morphism here. So we have that. And again, we would have associativity and other properties. So this thing is a category, okay? Now, to address the question you asked, first of all, is it okay if we have two objects and there is no morphism between them? Yeah, it's perfectly fine. We might have many objects which there is no morphism between them, no arrows between them. That's perfectly fine. But what about this case here? Do we have any two subsets? Does that happen here? So if in our example, if A and B are subsets of R, any subset of R, do we always have a continuous function from A to B, or no? Function between them. Okay, does anyone have any answer to this?
Not necessarily if one has like one interval and the other is two intervals.
So let's say A is the interval from 0 to 1, and B is the interval, say 0 to 1, union 2 to 3. Something like that. So question, is there any continuous function going from A to B or not? Yeah, that is correct. So we do have continuous functions here. We have a lot of them. So for example, suppose the function f of x equals x sends any point from 0 to 1 to the same point 0 to 1. It's not surjective, but it doesn't matter. It is continuous, isn't it? Or maybe an easier choice here would be just a constant map. Suppose a function which sends any x to just 0. the constant function. This also is a continuous function. Does that make sense? So here we have, if we look at the graph of the function, this is our domain from 0 to 1. And our codomain is 0 to 1, union 2 to 3. And the graph of the continuous, well, let's choose another value, so it would be better here. So say 1 over 2, doesn't matter, any constant point in codomain. The graph would look like this, the graph of this function, constant function. This is a continuous function. Actually, for subset of R, we can always choose the constant function. And the constant function here is continuous. So for example, someone says, what if B is the set of natural numbers? Yeah, again, the same thing holds. Always we can take the constant function. The constant function is always continuous, even if A itself looks disconnected itself. So maybe that's a good thing to know. So if A is, say, just natural numbers, and B is an interval, again, we can have a function f from A to B, which sends any natural number n, say, to a constant thing, say 1 over 2 in B. If we look at its graph, you would have, for example, say, let's assume n also contains 0, 0, 1, 2, 3, etc. So if you look at the domain is the set of these red points. The domain itself is so-called disconnected, right? 0, 1, 2, 3, etc. The codomain is this blue set from 0 to 1. And the graph of our function is just this constant map, which is just points above the domain. And it's 1 over 2 for each point. So although this function looks disconnected, but it is still continuous. Doesn't matter if a function is disconnected. Being disconnected does not necessarily mean the function is not continuous. This function is still continuous. So if you are familiar with the regress definition of a function being continuous, you can check that here. If you are not familiar with that, you can think about this question. Here, the domain being disconnected does not matter. Actually, it doesn't matter even if the function I'm choosing here is not constant. I could choose any other function. Actually, the result would have been continuous when the domain is disconnected. So the only, so I see that also in comments. So the only difficulty, the only case which we don't have a function is when one of these things are, one of these sets are empty, the empty set. So empty set is also a subset of R. Empty set is also a subset of R. And we don't have any map from empty set to another set, or we don't have any map from another set to the empty set. Okay, so as long as these sets are not empty, we're good. We have continuous map.
And from the empty sets to itself?
Yeah, so if we consider, one thing we can do is as our objects, we wouldn't even allow empty set. We say all the sets which are non-empty, for example. But if we want to allow that, well, this is a little bit fundamental problem. There are different ways to think about that. One idea is that you can just formally assume you have an arrow from empty set to itself. And because you don't have any map from empty set to any other sets, there is no problem of composition. So you can say in the set of, you can formally assume you have an identity from empty set to itself. It doesn't really matter. It's just something isolated. You have empty set and you have an arrow from itself to itself. Yeah, these are a little bit fundamental problems, and I'm not also very specialist, so I prefer not to really get into those. So that's one example. So let's see a non-example, something which is not something which is not a category. So for example, if I define C like this, so suppose the objects are again subsets of R. Okay, and suppose morphisms between any two subsets of R are functions from A to B which are discontinuous. Now the question is that, is C a category? So this time, rather than looking at continuous functions, let's look at discontinuous functions. Only discontinuous functions. Is that a category?
No.
Okay, that's correct. Why?
Because we just said the identity function is continuous, but if this is only discontinuous, then it can have the identity function.
Yeah, that's essentially correct, because, thank you. Yeah, because we wouldn't have an identity morphism. So there is no, well, that's not true that we would have identity morphism for every object. So let's write it like that. So maybe a very good thing to look is this one. Let's say A, is very specific example. Let's say A is the set which only contains 0. That's a subset of R, right? And right now, there is just one map from this set to itself, and that's the identity, right? It has just one element, and you have to send it to itself. So any map from the set which only contains 0 to itself is the identity, because f of 0 has to be 0. Right? This is the identity one, but it's not discontinuous. It is continuous. So this identity map is continuous, and it's not element of this this thing we defined here. So we don't have the identity, and therefore it's not a category. Yeah, that's correct. Now, getting a little closer to things we are doing now in this course in linear algebra. Suppose we have a field, let's say R, okay? And suppose we define a category, we call it vect R. This category consists of two things. The objects are all vector spaces over R. So here we have any vector space over R, okay? And for any two vector space, say V and W, the morphisms between them is the set of linear maps going from one to the other. So linear map. Well, now we want to show that this thing really is a category. Okay. So there are a few things we should check. One is that we have the composition. So if we have F from, say, V to U, well, maybe it's better to change their order. U to V and then G to W. We should have, in a category, we should have GOF. Here we have this because if F is a morphism here it means F is linear. And if G is a morphism here, it means G is linear. And we know that the composition of two morphisms, two linear maps, is another linear map, right? So here, G of F is another linear map, and therefore it is a morphism. Therefore, we have the composition of any two things. That's the first thing. The second thing is that we should have the identity map. So do we have the identity map? Well, yes, we do, because the identity map, again, is linear, right? So for any vector space V, the identity map from V to itself is linear. So we have the identity map. And it is really identity of composition. That's good. Also, there are functions, they satisfy the associativity rule, right? So everything holds here. And this is really a category of vector spaces. Over R, actually R doesn't matter here. Rather than R, we can take any field F. We have the category of vector spaces over any field F, okay? Is there any question up to this point? Okay. So another thing which, if you look at the graphs I was drawing in the beginning, you might guess, is that sometimes graphs are also, you can think about graphs as category. You know, by graphs, I mean just collection of a couple of points and a collection of, well, in this case, arrows between them. So something like that. So we can think, actually, these are called directed graphs. These things, these objects are also, you can think about them as category by taking the vertices as objects and these arrows as morphisms, as long as we have something like that, a cycle at each vertex. And also we have the composition. So if we have these two arrows, we have to have a third arrow like that. And I think what we have here is really, yeah. For example, we can think about it at this one as a category, okay? So these are a few examples. Let me think if we can. Well, the difficulty here is for you to getting to know category theory here is a little bit that usually in mathematics we go the other direction. Usually first we get to know, for example, groups, rings, manifolds, topological spaces, rings, modules, all things like that. And then we use category theory to find an abstract notion which unifies all of these things. Right now we are going kind of the other direction. You still have not seen these things. You might not be familiar with topological space, with a manifold, with a module, with a ring, with chains, with chain complexes, anything like that. So, but before that, you're getting to see what the object which is supposed to be unify all of these things. So it might be a little confusing, but I think it's actually a good approach to get to learn a little bit category theory. Okay, so let's see where we can go now. So maybe one thing, one other example is good to see before going to get to theorems is the notion of a group. So if you are not familiar with that, I would define it. So you've seen field before, so you have a sense of how one would define so-called algebraic structure. Group is another example of such a thing. So a group is a set with one operation, which is called addition. So when we got to know field had two operations. It had addition and multiplication. Group has just one operation. So in that sense, it's a little bit maybe easier to just state the axioms, which satisfies some properties. So for any two elements, A and B in the group, A plus B is also an element of this group. That's the first thing. It's closed under this operation. It satisfies the associativity rule, which means for any A, B, C in this group G, A plus B, if we compute that first and then add C, is equal to A plus B plus C. When we first compute B plus C and then we would add A. There exists an identity element for addition. I would show that with 0. It doesn't necessarily mean it's the same 0 as real numbers or natural numbers as we know it. It's an element in G. So there exists an element, maybe it's better to call it O, so you wouldn't confuse that with the 0 as we know it. There exists an element, identity element, such that doesn't matter how to add it to A, you would always end up with A for any A in G. And finally, for any element A, there exists inverse of A. We usually denote that with minus A, but it doesn't mean it's really minus A, because again, we are not working with real numbers. These might be a lot more abstract algebraic structures. So for any A, there exists another element. Maybe it's even better to show it with B. Let's not write A, such that this B is the inverse of A. So their sum would be this identity element. Any such a thing is called a group. Okay. Let's see some examples. For example, so examples of groups. For example, R with just the usual addition as we know forms a group, right? Because we have 0, we have inverse for any real number, say, I don't know, pi. We have minus pi, which if we add them, we would get 0. So we have inverse, we have everything, right? So is n with addition a group? Is this a structure? Does it form a group or not? Okay. Yeah.
We don't. Do we have the 0 element in n? We don't, right?
Well, let's say, okay, let's say we define n to have 0. It's a little, I think I'm not really sure. It's usually in more advanced mathematics, people assume 0 is an element of n. So let's assume that here. Okay. What about now? Is it a group now?
Well, there's an answer in the chat.
What is the answer? Okay, no additive inverse. That is correct. So for example, let's look at something here. So like 2. Is there anything which if we add that to 2, we would get 0? Well, there is. It's minus 2, but that minus 2 is not here. It's not in n. So if all of our world is just n, if you're thinking about this set, there is no additive inverse. So no additive inverse. So n is not a group. Okay, so that's that. So if you're leaving early, yeah, I'm gonna upload the whole thing on YouTube. I would share the link with you on Blackboard. So that's an example of a group. There are a lot of other examples we can think about that. For example, maybe one other good example to see is just Z2, which only has 0 and 1. This is a group, right? For example, for any element we have inverse. What is the inverse of 1, for example, in this group? What is the number which, if I add to 1, I would get 0?
1.
1 itself, yeah, 1 plus. What is the inverse of 0?
0.
0 itself. Yeah, and you can see it's really a group. So actually, group theory is really an active part of mathematics, just study of groups. Sometimes groups have this property that A plus B is equal to B plus A. In that case, it's called a commutative group. Sometimes that's not correct. Sometimes A plus B is not equal to B plus A. So it's not necessarily true that for every group we have commutativity. Now, the point is that we can think about any group as a category. So unlike the previous examples we had, we were not looking at one set, or we were not looking at one vector space. We were looking at all sets, or we were looking at all vector spaces, right? All vector spaces over R, for example. Here, I'm just talking about one explicit group. Any group can be thought of as a category. So suppose we have a group G. Suppose we have G a group. We can think about this group as a category. We can think about G as a category. And it's a little bit strange. It might be strange the first time you would see that. So I should say, if I think about G as a category, let's show that with C. I should tell you what are the objects and what are the morphisms. Can anyone guess what are the objects of this category?
Well, it's just the elements of G, because G itself is a set, right?
Okay, but let's try that. That's the most natural guess, right? Elements of G. Elements of G. So maybe it's good even to try explicit example. I would go back for a second. Just another example of a group is the set of integers with addition. This is a group. It is a group. Because now we have the inverse, right? The inverse of 3 is -3. The inverse of -4 is 4. So this is a group. And we have 0, everything's good, right? So we can even look at, so in your mind, you can think about G, for example, as Z, just one very explicit example, right? Yes. So if we take objects to be elements of G here, in this case, I would answer to that question, example of a group that is in ring after this thing. So think about Z. Elements of Z are like this: 0, 1, 2, etc., -1, -2, etc. These are the objects then. And then I should say what are the morphisms between any elements, X and Y? What are the morphisms between two things? For example, what are the morphisms from 0 to 1?
Well, they require a binary operation. So if we're just taking morphism X to Y, that implies like singles. So I guess maybe not the elements of G, then be the object, but G itself.
So I didn't get that. Let's focus on something explicit. For example, here, what are the morphisms from 1 to 2?
Like 1 plus 1 like equals 2. So morphism would just be an additive of 1 and the unspecialized number 2 minus 1 such that it makes 2.
Yeah, you see, that is correct. But at the end, when we are constructing a category, we should have kind of a well-defined notion of arrows. Like, when do we have arrow from 1 to 2 or not? What you're saying might work. I need to think about that a little bit more. But actually, this is not the category which I have in mind and usually is used. This direction might actually work that you are suggesting. We can think about that more. But the kind of common thing is, whenever you have a group, you can think about it as a category, which the objects of that category is just one consists of one element. I would just show that with 1 dot. Doesn't matter what the group is. The objects is just 1 point, 1 object. And I should say, what are the morphisms? Well, I just have 1 object, so morphisms, all of them are from this object to itself. Now, the morphisms are the elements of G. Okay. So listen, guys, this is, I'm going to finish this in 1 or 2 minutes. So for example, let's see how does this thing work. For example, suppose our group is Z with addition. Okay. So I'm saying the categorical way to think about that is to say this is category of just 1 object. And every element in our group is a morphism from this thing to itself. For example, 0 is an element here. It's a morphism from this thing to itself. 1 is another element here. It's another morphism. I don't know, 59 is another thing in Z. It's another morphism. Minus 2021 is another morphism. Any element of G would be a morphism from this single object to itself. It has identity. And how would I define composition of maps? So remember, when we have 2 morphisms, F and G, we should have FOG, right? So here, for example, if we have, I don't know, if I take this morphism 1, this one is a morphism here, and I take this other morphism 59, I should define their composition. Maybe, here I really mean composition of 1 and 59. How should I define that? Well, it's easy to guess, right? What should that be?
60.
I would just define their addition, which is 60, which is another morphism which exists here, because every element of our group, which here is the set of integers, is a morphism here. So it's kind of weird, because you would think, if you want to think about the group as a category, the elements of the groups should be the objects, but actually it's the other way around. The elements of the group should be thought of as morphisms, not objects, because we can't do anything with objects. There are morphisms which have composition between them, and composition between morphisms correspond here to additions between elements in the group. Yeah, so, okay, is there any question about, is there any question here about this construction? Thinking about these things as a category, does that make sense to everyone? Okay, so there's a question here, example of a group which is not a ring. For example, the permutations. Permutations on n elements is a group, it is not a ring. We can talk about that more next time. So a very good reference to learn category theory better, let me just introduce this reference as the final thing. Is, well, if I pronounce it correctly, it's so as a reference, I really recommend Category Theory in Context by Emily Real. And there are a lot of YouTube videos you can look and watch and kind of get a better feeling about this thing. Okay, I think our time is up actually. It's 5, I think I'm 5 minutes over time. Is there any question? Okay, so if not, let's stop the meeting here.